Hello, hi, good afternoon. So, my name is Kataji Ha, and then my talk title is Cilia-associated oxysterol 7-beta-27 DHC is required for polycystin activation. And here's the activity disclaimer and disclosure. And I'd like to introduce myself for the first time in the public. My name is Kotaji Ha, and I'm a research associate specialist in UCSF. My research is focused on the regulation of a polycystin complex in the renal epithelial cells, and I specialize the ciliary patch clamp technique for the precise measurement of ion influx across the ciliary membrane. And to save our time, here's the LinkedIn QR code, so you can take the pictures and then you can connect me. And then today's talk is actually available as a preprint form. So here is the QR code for the bioarchive. You can download my paper and then read. If you have any questions, please email me. And this study is submitted to Nature Chemical Biology. And I'd like to introduce about primary cilia. Formally, it's super exciting. So primary cilia is a special organelle found in the surface of the cell membrane, very small, hair-like. So it plays a role to receive the signal from external side of the cell and then deliver the signal to the cytoplasm. But I want to play with a number a little bit. So the diameter of the primary cilia is 400 nanometer, and the length is 5 micrometer. But the number doesn't give you an idea, right? So I prepared the full view. So did you detect the cilia in the image? It's right here. And I'll give you the full view here. This is how cilia look like, and my job is to use the glass pipette and grab this primary cilia and detect the ion movement across the ciliary membrane, and that's what I do. And then cilia can be found in our body system, in the brain, fibroblast, eye, and ventricles. And today we're going to focus on the kidney tubule primary cilia. So as we know, the polycystin complex, PC1 and PC2, when we have a mutation, it leads to the ADPKD. But so polycystin complex, they form a non-selective cation channel. They expressed in primary cilia, and then they conduct sodium, potassium, and then calcium across the cilium. But it's really hard to study because not only because of the large size of this protein, but also they specifically localized in the primary ciliary membrane, and it's really hard to patch clamp that. As you can see, it's very teeny tiny. So to tackle this problem, so here's what we did. So polycystin complex do not express on the plasma membrane. It only traffic to the cilia and then conduct ion. So what we did is this. So here's a construct, and we added the signaling peptide in the N-terminus of the PC1, and then we enable polycystin complex to traffic to the cell membrane. With that, there's an easier screening available, so we can just patch clamp the whole cells. And then after we confirmed the polycystin expression in the plasma membrane and also ciliary membrane. So after confirming the expression, here was our question. So can we record the polycystin complex in the cell membrane? So here's another question that we wanted to tackle. The polycystin complex, they are active in the cilia membrane. However, when we express the polycystin complex in the cell membrane, it's quiet as a wild type. It's intact polycystin complex in the cell membrane, but it's quiet unless we introduce the gain of function mutation in PC2. So what's the difference between the plasma membrane and ciliary membrane? Because there's something special within primary cilia, and it activates the polycystin complex. We wanted to answer this question. So we paid attention to lipid compartmentalization system. Previous study, they reported that some lipids or cholesterols are enriched within primary cilia. So some PEEPs, PEEP4, PEEP4-5, and specific oxysterols and cholesterols are enriched in primary cilia, and we decide to test it all of them to see if they can make polycystin complex active. So we injected those PEEPs and cholesterols and oxysterols into the cytoplasm and then recorded the polycystin complex activity. It was still silent unless we found the 7-beta-27 DHC. And this one, we were able to detect the channel activity as a wild type in the plasma membrane for the first time. Here's what quantification looks like. So oxysterol 7-beta-27 activates the polycystin complex in the plasma membrane and in a dose-dependent manner. It was quite surprising. And then after we found the activation, we wanted to know how this lipid can modulate the channel activity to conduct the ion into the cells. So we played the molecular simulation. So you can see this video right here. So we simulated oxysterol binding, and we treated the oxysterol in the cytoplasm, and we were able to find the two key amino acids in the PC2 subunit, which is glutamate 208 and then arginine 581. We hypothesized that these key amino acids form a lipid binding pocket in PC2. And we mutated this amino acid into alanine, and then we confirmed their expression. And even if these amino acids are mutated into alanine, it still beautifully traffics to the ciliary membrane. And what do we do next? We recorded these mutations. So we overexpressed these two mutations in PC2 knockout cilia, and then we found that these mutations impaired the ciliary currents. So activity is gone. And then we also treated this oxysterol 7-beta-27 in the cilia and then measured the polycystin activation. It turned out that this oxysterol further potentiates the channel activity. So now we learned that this oxysterol can potentiate the ciliary currents. But what if there's no oxysterol at all in cilia? What happens, right? So we decided to study the oxysterol synthesizing enzyme in the renal tubule. So in 2021, there was a proteomics paper saying that this HSD11B oxysterol synthesizing enzymes, they're expressed in the nephron, especially in the proximal tubule and then collecting duct. So we treated the carbenoxolone to inhibit this enzymatic activity in the renal epithelial cells and then measure the polycystin complex activity. And we found that carbenoxolone treatment impaired the ciliary currents. To find the physiological meaning of this study, we injected carbenoxolones to newborn mice using IV and IP injection. And we found that carbenoxolone injections result in the significant tubular dilation in the mouse at early stage, around like P17. So here's a summary of my study. So polycystin complex is an active channel within primary cilia. However, it's inactive in the plasma membrane. It's because there is an oxysterol-associated cilia-associated oxysterols in primary cilia, and that activates the polycystin complex. And when we injected this oxysterols in the cytoplasm, we were able to detect the channel activity. However, when we inhibited this enzymatic activity to inhibit the oxysterol synthesis, we also found that ciliary channel activity is interrupted. To find the physiological meaning of this, we injected carbenoxolone to the mouse, and then it resulted in the tubular dilation significantly in the mouse. So I'd like to thank my team for this study. So my friend Nadine and Aide, they helped me to perform the imaging analysis and animal study, and then Paola helped me to perform the molecular simulation study. And I also like to thank Dr. Jeremy Ryder and then Gabe and then Dr. Mion Park to supervise all my study. And I also like to thank for PKD Foundation and NIDDK to support my research. Without their help, I couldn't conduct this research. And I'd like to thank Alice for inviting me over here, and then the technician Lee who helped me to practice my talk before this session. So thank you so much, and any questions are welcome. And thank you so much for listening to my talk.
Thank you so much, Vishal.
Beautiful presentation.
Thank you.
Could you tell us if the activation is seen only with the PC1, PC2 heteromeric complex, or does the PC2 homomeric complex also gets activated with this oxysterol?
That's actually a super amazing question, because we actually did that for the paper.
Yes.
I can answer the questions. So this PC1, PC2, they form a channel, but then PC2 alone can also form a channel in primary cilia. So we tried the oxysterol in the PC2 only expressing cilia, and actually PC2 itself is a super activating, so I couldn't really find a significant activation. But when they have PC1 and PC2 expression, it significantly activates the ciliary channels.
And a quick follow-up, is there a way to deliver this oxysterol as a therapeutic in, for example, preclinical animal models?
That's a really good question, but working with oxysterol is quite hard because it doesn't have biosensors, right? But what I suggest here is this binding pocket, the lipid binding pocket, this is the channel modulating site. So when we develop the activator for the polycystin complex, it can help to modulate the channel activity. It can be used as a therapeutic target.
Yeah, great. Yeah. Thank you.
Thank you, Vishal. Hold on.
Thank you so much. Great work. So as far as I understand, the enzyme is 11-beta dehydroxygenase?
Yes.
Okay. And in nephrology clinical practice, we know that the licorice blocks this enzyme.
Yes.
Is there any clinical data or study or any other data it is associated with cyst development or
That's super interesting, because that's also the challenge that I'm tackling right now. Because, as you notice, this enzyme is related to the glucocorticoid receptor and mineralocorticoid receptor. It's quite hard. So to find the link, so we are injecting the carbonoxolone to PC2 heterozygous mouse line to see if they form a severe phenotype. Yeah. So we can find the connection between the carbonoxolone and then.
But we don't have any clinical licorice associated.
Yeah,
with,
not that I know of yet.
Okay.
Yeah.
Gotcha. Thank you.
Oh yeah, sure.
Okay, do we have any other questions in the audience? I think Elise is checking the online QA. Okay, perfect. Thank you so much, Dr. Ha.
I'm sorry, I have to go all the way to QR code. Sorry. Here we go. Yeah. Thank you so much.
All right. So our second speaker is Dr. Sarah Gugaski from the University of Cologne, and since that is in Germany, we have the speaker is not actually here, and she has pre-recorded the session, and we will hear the results from the keto ADPKD study through that way. So.
And thank you very much for having me in this session.
Create an amazing website with Fiverr.
And thank you very much for having me in this session that I am aware is of great interest not only to the field but to patient community. So I'm very happy to give you an insight on the work that we have done here and especially focus on our latest trial, Keto-ADPKD. There is nothing I personally have to disclose. Our study was funded by PKD Foundation as well as Marga and Walter Ball Foundation. My talk focuses on ketogenic dietary interventions. So first, what is ketosis anyway? When glucose is held from our body, it is able to switch to a metabolic state that provides additional energy in the form of ketone bodies. And there are several ways to go there. For instance, just totally withholding any food and fasting state, or a classic ketogenic diet containing an increased fat, strict reduction of carbohydrates, and maintaining a normal protein intake. One of the first steps into this field was showing that restricting caloric intake reduces cyst burden in PKD animal models. But what is the mechanism behind this and how can we use this? The group around Torres and Grimes stated that caloric restriction in mice must lead to ketosis. But why is that? Well, if mice get less food, they tend to eat everything they have at once, and this leaves them basically with nothing, so they fall into a natural pattern of time-restricted eating. The focus of the group was to investigate if ketosis rather than calorie intake was responsible to stop renal cyst growth, and they made a pretty strong case with their publication in Cell Metabolism 2019 that identified ketosis to be the decisive factor, and that also feeding ketone bodies, even without any change in caloric intake, was favorable. So they figured that cystic cells must be metabolically kind of inflexible, which means that opponent to other cells, they cannot simply switch to running on ketone bodies and fatty acids, but are dependent on glucose. So this work received a lot of attention from the scientific and clinical field, but also from patients who ask themselves and caregivers, should I follow a ketogenic diet now? Of course, each person freely chooses where their eating habits are, and people have always been on diets, have always been on ketogenic diets for a long time, but this was out of their own motivation, such as losing weight. We do have data on children that were treated for epilepsy, but we lack data for ADPKD patients, and just in general, we cannot base any medical recommendation based on preclinical data. So here we need a sound evidence from clinical trials. This is basically when and why we set up a translational pathway for ketogenic dietary interventions in ADPKD. And in fact, we started with surveys and retrospective case studies that relied on those individual experiences from patients who just went on a diet themselves. And step by step, we set up a randomized controlled trial setting. Due to the time frame given here, I focus on our latest unpublished trial after just very quickly talking about the former study, Reset PKD. Here we enrolled 10 patients for a ketogenic dietary intervention of only 2 weeks. Here 90% of participants reached ketogenic state and rated the diet as feasible. This time frame was not sufficient for an impact on TKV, but however we saw a change in liver volume. We are very cautious about that because we concluded that this might rather not be due to the cyst fraction but to a depletion of glycogen. So we went on to Keto-ADPKD, a first randomized controlled trial, and we enrolled 63 patients in 3 arms. The control arm, a classic ketogenic diet arm, and a 3-day water fasting every month. So the intervention phase was 3 months this time, and we had 1 month of a run-in phase and 1 month of a washout phase. We finished the trial just last year, and the paper is under revision at the moment. So hopefully the full set of data will be available very soon to everybody. For today, I picked 3 key points among a very wide range of analysis that we did here. Feasibility was one major interest. To assess this, we used a questionnaire basically asking for well-being and how the diet could be implemented in everyday life. The answers were scored from +4, meaning this was very well doable, to -4, this was not feasible at all to me, and an overall score of 0 or higher was considered feasible. This could be reached in both intervention arms, and we combined this with measuring of beta-hydroxybutyrate and acetone to see if the patients also stick to the diet and not just said, this was very easy. So we measured beta-hydroxybutyrate in blood for the ketogenic diet group versus the control group, and as you can see in the dietary intervention led to a clear-cut increase in beta-hydroxybutyrate levels. For the water fasting group, we measured breath acetone levels with a device that could be easily used by patients at home, and here we also saw an increase during the 3 days of fasting. We obviously were very interested in kidney function parameters. When we looked at eGFR, we did not expect a strong signal in this rather short period of 3 months' time. However, in contrast to both other groups, an increase of eGFR from baseline to end of diet was statistically significant for the ketogenic diet group. We saw that the effect was reversible after switching back to a normal carbohydrate-rich diet, and this rose a couple of topics. The key question being, could this be just increased meat intake, or could the muscle mass be decreasing? One way to look at this is by using an alternative marker for kidney function apart from creatinine by repeating the analysis with cystatin C, which we did, and here we found very similar results. We also included body composition measurements, and the changes here show that it is mainly fat mass and not the muscle mass that decreases. Of course, hyperfiltration is always a concern when we have eGFR increases. We looked at albuminuria, however, that did not change. We looked at blood pressure as a surrogate for hemodynamics that did not change, but we are clear that we are not able to rule this out based on so little data. What we do believe is that those acute effects are maybe due to changes in inflammatory profile and also changes in pressure within the cysts that relieve the rest of the tissue, and that might play a role here. So what we definitely will have to look at are long-term effects in longer trials and also rebound effects. Another very important aspect to focus on are side effects. We documented well-being of our patients throughout the study, and overall this was reported to be very well. Let me just highlight 2 points. Uric acid went up in the ketogenic diet, which is something that we well expected within the diet. In our cohort of ADPKD patients with high risk of kidney stones, as it is, of course, we have to be very attentive. And we had one patient in the ketogenic diet group that developed a symptomatic kidney stone while being on the diet, but whether this was causally related is not clearly accessible in this very small cohort. But it is something that needs further attention in the future trials. Further, we definitely need to think of preventive factors such as citrate supplementation. The other key point is cholesterol, which also went up in the ketogenic diet arm and was also expected from published data. But figuring out whether this effect is transient will be important for evaluating of long-term ketogenic interventions. What is more important now is the question, what does this even mean for the cardiovascular risk? So the existing data on this were not at all very clear to us. So to address this, we added a full NMR lipidomics panel to resist, amongst others, a lipid particle size assessment that plays a major role here. This all is added and discussed in our final publication. But overall, we could not find any strong signs leading to an unfavorable lipid profile. I'd like to finish by giving a very short interpretation of the data from our point. It is important to highlight for us that we are not there yet. I'm sorry. But when we look at our pipeline again, even if this does not picture the situation 100%, since we do not have a pharmaceutical study here, we are about here now in a phase 2-like trial section. And yes, we might be driving rather a Volvo than a Ferrari, but this is to make sure safety of patients are our highest values. So keto ADPKD, in our opinion, does not signal to any relevant safety issues that limits any further studies. It is anyway also not designed to show that KD does work at the moment, but it makes us very confident that it can work, and not only paves the way for further trials that are definitely needed. It makes us want to go there as soon as possible. So yeah, let's go. And this leaves me only to say thank you so much for your attention and for having me. And we would like to thank the whole study team, the collaborators, and ADPKD Cologne, as well as PKD Foundation for your support. And last but not least, we had amazingly motivated patients who made all this possible. So thank you very much. For any inquiries later on, just send me an email, find me on Twitter, or send an email to our department.